Okay, then we will get started. Hey, everybody, my name is Jordan Last. I am the CEO and I'm a co-founder of a company called Demergent Labs. We are building fundamental open source developer tooling on the internet computer. Azle is probably our flagship project, enabling TypeScript on the internet computer. So I guess, let's intro the rest of the team. So it's not just me. We actually have three co-founders and engineers. Dan, do you want to also introduce yourself?
Yeah, hi everyone. I'm Dan Starin, and co-founder of Merchant Labs with Jordan. And yeah, just working on Azle. Very excited to have you all here, and hopefully we can answer all your questions and get you going.
And Benjamin.
Hi, I'm Ben DeMan. I don't know what more I can say that Dan hasn't already said more beautifully, but yeah, I'm here and happy to help and happy to see y'all here.
Cool. Yep. So that's the team. We basically work full time on Azle and the Python SDK as well. So everything's good. Can I get an audible cue that this is all showing the slideshow?
Yes.
Yes.
Sweet. Okay, so yeah, like I said, we are Demergent Labs. You just met all three of us. We want to accelerate the adoption of Web3, the internet computer, and sustainable open source software in general. The whole Web3 portion of this bootcamp really focuses on the platform that is known as the internet computer. If you want to learn more, there is a ton of material at internetcomputer.org. There is a ton of material at Dfinity.org. Dfinity is the foundation that created the internet computer. And there's also a very, very lively developer forum. I think forum.dfinity.org with a ton of information. We'll just go over some basics here. What is this thing? The internet computer, I think, is best described, from my point of view, as a general purpose, decentralized cloud platform. I think we've all heard the term cloud before. If you are not familiar with what the cloud or a cloud is, it's basically a managed, server farm or warehouse with a bunch of software that makes it easy to deploy web applications. The biggest clouds that we know of would be Amazon's cloud, Microsoft's cloud, Google's cloud, and there's a smattering of others as well. And basically, these companies have a whole ton of computers of all different sizes and capabilities, and then they have a suite of software tools that allow you to deploy your web applications and make them available to the entire world. And they have all kinds of scaling tech and all kinds of crazy stuff. So that's the kind of the lay of the land for cloud as it is today. The internet computer is decentralized. That is the big difference. It is, or maybe better said, a progressively decentralizing cloud. It's not owned or controlled by one entity. It's not just Amazon's cloud or Google's cloud. It is a cloud owned and operated by independent data centers and independent node operators inside of those data centers. And one of the main purposes of a decentralized cloud, I mean, any cloud, any application developer wants their applications to be secure, right? And me and my team have been thinking a lot about this. What does it mean to be secure? What do you want? What properties do you want to be secure when you're deploying, I mean, basically any kind of application? And we think it probably comes down to at least these three main properties. One is confidentiality. That's basically privacy and authorizing access to data. You don't want to put data up on one of these cloud platforms and just have the entire world be able to read it necessarily. You want to be able to authorize that. And the internet computer, its confidentiality story is not the best today, but it is better than other blockchains. And there's stuff coming that will hopefully, I mean, I guess in our wildest dreams, but they're working on it, allow us to have general purpose confidential computing, which would be quite amazing. You also want integrity. You don't want any changes to your data or your state unless they're authorized. So, for example, if you put up a website, you generally don't want anybody to just come and change it. Even Wikipedia, which allows general purpose changes. I mean, they have a whole ton of rules and they have a whole ton of different authorization strategies to keep that website with integrity. And so we also want ours to have integrity. Availability means that your application is always up and accessible. And these three things you would generally want, I think, from your application. And a lot of things I think are subsets of these three properties. For example, censorship resistance might be a subset of availability because you don't want people to shut down your access unless they're authorized to do that. And how does the Internet Computer achieve this security? Through something called Byzantine fault tolerance. And that's really what all of these decentralized computers and the Web3 space, I don't want to say it's about Byzantine fault tolerance, but so far, this seems the best way to achieve the properties that we want from our applications. We want to be able to support a certain level of faults in these networks. And a Byzantine fault is just basically an arbitrary fault. You don't know if the node is just faulty. You don't know if the operator is incompetent. You don't know if it's just shut down or if it's malicious. Byzantine fault tolerance is probably the highest level of fault tolerance you can have. And from that fault tolerance in a decentralized network, you gain a super high level of security. And the Internet Computer provides that, and there's papers on it, and you can go read about that if you're interested. It's something very interesting about the Internet Computer. So far, Byzantine fault tolerance, most blockchains most blockchains and decentralized computers are going to have that confidentiality, integrity, availability. Everyone's trying to get to those. The Internet Computer is quite unique in that it is actually horizontally scalable through something we call sharding. And a lot of blockchains are trying to become sharded. Ethereum is doing its own type of sharding. There's all kinds of experiments, all kinds of different ways of people trying to do this. But to my knowledge, in my opinion, the Internet Computer has really figured out horizontal scalability or sharding. I would almost say it's objectively better in most ways. At least the developer experience is quite nice. You use normal, async await type syntax that you'll be used to from JavaScript, C#, Rust, and it actually works. It does increase latency, but it actually works quite well. It's also a WASM runtime at its core. So this bootcamp is focused on TypeScript and JavaScript, but you can also run Python. You can also run Motoko, the language created by Dfinity for the Internet Computer. You can also run Rust, and in the long run, anything that can compile to or run on top of WASM will be able to work basically on the Internet Computer. And other blockchains have this as well, but not all. So the Internet Computer happens to have it. And here's an absolutely giga level difference between the Internet Computer and other blockchains is that it has giga level compute resources. By that I mean you have gigahertz of CPU, right? Billions of cycles or instructions per second, something like that. Gigabytes of heap. So if you want to write into global variables or just store information, like in Ethereum, when you just want to store your operating stack, basically, I believe would be the analogy in Ethereum. That thing is really small, probably kilobytes. The Internet Computer really does give you gigabytes of heap. Not sure how big the stack is, but I would imagine quite large. And gigabytes of storage. Right now, 64 gigabytes of something that we call stable storage that we'll definitely get into later. I think it'd be incredibly difficult to find any true blockchain with Byzantine fault tolerance and similar level of security that would have this level of compute resources. And our team we're trying to come up with a framework so we can go analyze tons of different blockchains, and hopefully we'll be able to do that and publish that information. But right now, just think of the Internet Computer as something that does give you giga-level compute resources, much more similar to an actual cloud platform. And of course, this doesn't all necessarily come for free. There are some trade-offs. The Internet Computer does not have what we refer to as global consensus. So all the nodes don't know about all of the state and all of the applications. The network, in fact, is partitioned into sub-networks, and each sub-network runs its own consensus. And the sub-networks communicate with each other through a signature scheme, a BLS signature scheme, and they call that whole concept chain key. You can also go look into that. And there's small replication. We don't have hundreds of thousands of validators or even hundreds of validators per subnet. Right now we're at max 40, and a lot of application subnets have 13, and etc. There are more trade-offs, and these things are extremely nuanced and very technical in nature. But just know that the Internet Computer has its trade-offs. Ethereum has its trade-offs. Bitcoin has its trade-offs. Everybody is trying to find that sweet spot, and the Internet Computer really leans towards that giga-level, horizontally scalable general purpose cloud platform. And now to introduce you to Azle and Kyber. Again, this bootcamp is focused on Azle, but just so you know, Kyber is the Python CDK. Everything you want to know about Azle, if you do want to just study on your own, can be found at github.com/demerchantlabs/Azle, and that gives you a link to the Azle book, which we'll get into. And I think that's where that presentation ends. Now we will jump straight into actual development. I just did want to show you the repo here. Here's the URL again. And yeah, if you guys could post that in the chat. I know these resources are all over, but maybe make it easy for them. Here's the repository, and I did want to focus in on something real quick. The nature of Azle. It is beta, and I'll just read the disclaimer. Azle may have unknown security vulnerabilities due to the following. We don't yet have a ton of live successful continuously operating applications. We have a lot of tests, quite a few, but we do not have the very, very extensive property-based tests that we would like to have. We do not yet have in-depth security reviews or audits, and currently our engine is experimental, though basically right now we are literally working on swapping the engine out for a much more mature engine that will be more performant and have fewer bugs and potential issues. So it is beta, but it is quite functional right now, and if you have questions about that, we can answer hopefully every concern or question you might have about that. And then our roadmap, in case you're interested, we are doing this right now. We are swapping out the engine, again, for performance, for security, and for stability. Once we have that swapped out, we really, really want to work on broad NPM package support. So we want you to be able to NPM install as many packages as possible. Right now, there are definitely packages that work, but there are a lot that don't work. That's a combination of Azle just not having the APIs implemented, and also the Internet Computer not providing the functionality. So the Internet Computer, though it wants to be a general purpose cloud platform, it has not achieved the vision yet. And so there are certain concepts that simply do not port over. But I mean, hopefully we can get a lot of these out there. Probably the biggest limitation the Internet Computer will have, if you're used to Node or something else, would be networking. So the HTTP requests, sockets, and all that kind of stuff is a lot different and quite limited to what you would expect. It's a lot better than what you get on another blockchain like Ethereum, but not quite as good as what you get from an actual cloud. And then once we have this, you guys should be able to do a whole ton of stuff, and then you'll just be waiting on us to really battle harden the Azle compiler and everything under the hood. So the repo, I don't know, it's not that interesting to you unless, no, it is. The examples directory in the repository. If you ever want to know how to do anything there might already be an example written. Some of them are quite simple, but they at least show you the API and show you how to do things. So we have just tons of these things, like something like 60 or 70 examples showing you how to do all kinds of things. So this is an amazing resource for you. And finally, the Azle book I will show you, which is linked to from this main repo documentation. It's all about the Azle book. Here is the Azle book. This is designed to be an in-depth guide to developing your canisters in TypeScript on the internet computer. Each of these chapters we put in a very specific order. We believe this is a very, very good way to learn about not only the internet computer, but canister development, and each concept is going to build on the other concepts, piece by piece. So again, if you want to be self-directed, just jump into the Azle book and start reading these chapters. Let me point out chapter 2, because so far we've been talking a lot about the internet computer itself. Chapter 2, we really try to show, very transparently what the benefits of Azle and the internet computer are, and then also, let's see where it is, also what the drawbacks might be. So we put a lot of effort into, just kind of spelling that out for you. So if you're interested, come over here and read chapter 2. And now let's get hands-on. So these are the prerequisites. If you want to get started with Azle, you really need to have some kind of a Unix-like environment. Either your machine is Linux or Mac, or if you are using Windows, you really need to make sure to install the Windows subsystem for Linux. I need to have Bash on there. So Linux, Mac, or the Windows subsystem. Once you have these installed, you need to install Node.js version 18 and then DFX version 0.14.2. You might be tempted to install Node.js from the official website, but I highly, highly recommend you do not do that. Instead, please use this tool called the Node Version Manager. There's, the link is all here. Very, very simple to use. And once you have Node Version Manager installed, it is dead simple to install and switch between different Node versions. So highly recommend using NVM to do this. And then you need DFX. DFX is the developer tooling. It's the CLI for the internet computer, basically, created by the Divinity Foundation. And I highly recommend you use version 0.14.2. Really try to stick to the exact versions that we show you in here. If you really know what you're doing, you can probably mix and match versions. But if you're just starting, I don't see why that would be necessary. So these are prerequisites. Also, I highly recommend using good old Visual Studio Code as your programming editor. Visual Studio Code is not necessary. You could use Atom or Notepad++ or whatever you want, but VS Code is very nice. The purpose, though, is to just have a text editor where you can write your code. I think that's it. So now we'll move on to chapter 4. Hello world. There is a quick start and there is a methodical start. The quick start is quite simple. You just run this command in your terminal. So go to your terminal, npx azle new, and then you type the the name of your project. So let's go ahead and run that. If you have nothing else installed, this will create an entire new project for you. You just go and add it to VS Code. And here it is. Everything has been created for you. The methodical start, by the way, is just going to go through step by step everything that we're about to go through right now. So we'll just go with the quick start and walk through each of these files. So I want to point out that Azle projects, we are trying to make it as familiar as possible to a web developer. within reason. So a lot of these things you will already be very, very familiar with. For example, this is a tsconfig file. If you are already a TypeScript developer, you already know this file. These are the settings that we recommend or require for your project to work. You can just copy paste this every time. Nothing too crazy here. And then the package.json, you don't even need all these crazy scripts. Those are just to help you out if you want them. But the main purpose here is to add Azle as a dependency. So we actually do need to run npm install. So now that we have a package.json with our Azle dependency, let's actually install that. And I mean, it's work. This is just straight up npm. We're not using anything special or different. This is just the npm tooling. npm comes with Node, by the way. Once you install Node 18, you will also have npm if you used nvm to install it. And running npm install, of course, creates our package log file. You should already be familiar with this if you are a TypeScript or a web developer, but basically this is going to really lock down your version, so it doesn't matter. You can always reproduce the same exact node modules folder on any machine in any environment, basically. We have our good old git ignore, just ignoring some files and folders. And then we have the first thing that is actually different about the Internet Computer, a file called dfx.json. This is the configuration file for Internet Computer projects. Quite simple. It is just a JSON file. The keys, at least for the canister property, the keys are just going to be the canisters in your project. So in this case, we have one canister or one application that we're deploying, and it's called Hello World. And you just have to fill in these fields. Generally, you can just copy paste this and basically just change the name. So if I wanted a new canister called new canister, I would just change all those names, and it should work. We are working to simplify this greatly, by the way. I'll just show you a sneak peek of what is coming. Eventually, hopefully very soon, we'll be able to say type Azle main and just pass in the path to your main file, and this will be it for the most basic configuration. But we are waiting on some underlying tooling to be built to do that. So for now, you just need to do the slightly more complicated way. Again, copy paste is not too crazy. If we go into our source directory here, you will find the actual application. So here it is in all of its glory. This is probably the most simple application you can make, right? We have our imports from the Azle library. This library is going to give you access to basically all of the Internet Computer APIs that your canister needs. In this case, we need two. We call these annotations. They are kind of a not quite a special syntax, but unfortunately, TypeScript does not allow you to use decorators like this. This is what Python or other languages would probably use. We can't use those outside of class, and classes in this case provided a bunch of complications that we were not comfortable with. So we created this special thing called an annotation. You're going to just take these annotations and you're going to mark your functions with them to provide special functionality to your functions. In this case, we have one function called getMessage, which is marked with the query annotation. This makes it what we call a query method. A query method, if you just want to keep it really simple, is a read-only method. If all you want to do is read some state, then mark your method or your function with a query annotation. In this case, all we're doing is reading this global variable called message. Whatever string is written into this will return it. It will also return it very, very quickly on the order of tens or hundreds of milliseconds. And that is because a query method does not participate or go through the consensus process of the Internet Computer. Remember, we talked about Byzantine fault tolerance and being a decentralized cloud platform. And we talked about the security property of integrity. Query functions do not have the same integrity as update functions. So let's talk about this update function or method here. Notice we are actually changing the state of our canister. We receive.
Just before
go
that, someone is asking if you can zoom because the phone
Oh,
starts.
yeah. Okay. Is that better?
Yep.
Okay. So yeah, this set message function is an update function. And notice we are receiving a parameter, which is a string, and we are setting this global variable called message to whatever this new string is. So this is not a read-only function. This is a read-write function. We can actually write to the canister, and those changes will be persisted. And those changes will have integrity, and they will go through consensus. They will have integrity because they go through consensus. So all the nodes in your subnet will basically execute the same function behind the scenes for you and ensure that, at least 2/3 of them agree on the change, and then that will be persisted. So that's going to take a few seconds to complete. So together, we basically have, one of the simplest databases that you can create. It's just a string, and you can change that string at will. So that's that. Nothing too crazy. Now, what we want to do, I'll zoom here as well. Now that we have our application written, we might want to deploy it to the internet computer. We are going to focus on deploying to a local replica or a local node, basically running on our machine. You're going to want to do most of your development locally because it's free. You don't need ICP or cycles to run it, and it's going to be quicker and just easier to run tests and do everything locally. So to do that, we're going to use the dfx command that we installed earlier. We're going to run the start. The start command. It is a very good idea to run it with the clean option. If you ever have, I don't know, just weird problems or issues with the canister, tack on this clean option, and that will just kind of, restart everything and wipe the state of your canister. So, I already have this running somewhere, probably over here. Sorry about that. It should take a couple seconds to boot up, and boom. So in this terminal, I have a local internet computer node running. I'm going to just leave that running because there's going to be logs, and I might want to turn it off, turn it on. It just makes it really easy to have over here in the terminal. Then I'm going to open up another terminal and zoom in for you. And now I'm going to deploy my application. If all goes well, running dfx deploy will just work. It will compile everything down to WASM, basically, and deploy that WASM module to the local replica. So I already have Azle installed, so the compilation process is quite quick for me. Just be aware that the first time you set Azle up and everything, it is going to take a few minutes. So do not be surprised if it takes like 5 to 7 minutes for your first deploy. Okay, so everything went well. The canister has been deployed. I'm not getting any errors or anything over here. So now we can interact with our canister. There are two main ways to interact with the canister locally. One is from the command line and one is from the browser. The browser way is really nice. So you can just copy this URL here. Okay, so notice it has pulled up a little nice UI representation of every method in our canister. So for get message, for example, I can actually query it as much as I want. It returns very quickly, and notice it is an empty string. And so now we can call set message to actually write into that string. And notice it took a little bit longer because of consensus. But now if I call get message, boom, hello world is there. So pretty cool. You can also do this from the command line. If I want to call a canister from the command line, I can run dfx canister call, the name of the canister, and then the name of the method. So notice hello world, and then I can also set that to something else. And then I can read it again. There you go. It's changed to something else. And over here in the browser, it's changed to something else. So that is the whole process of basically creating a canister, deploying it, and interacting with it. There are a couple new things over here. One is this new file that was automatically generated for you. This is your Candid file. We will dig into this a lot more later, but Candid is an interface definition language for the internet computer. It's basically a domains. I guess it's relatively general purpose, but it lets your canisters define their methods with all of their parameter and return types, and it makes it really easy for canisters written in other languages, clients written in whatever language and running on whatever platform. It makes it very simple for all of these different clients basically to interact with each other, because everybody knows what the types of everybody else are. This file is automatically generated for you. You do not need to write by hand. In fact, you cannot write it by hand. It is just done for you. But if you ever want to look at it, it's going to be wherever you define it to be. In this case, we said it was in source index.did. Also, there are a few more directories created here. The .dfx directory is created when you run dfx start. I mean, generally, you shouldn't really have to go look in here. Though, if you do want to find the IDs of your canisters when they're deployed locally, you can look at this canister IDs.json file, which is convenient. And there's also a .azle directory created for you. If you do want to see the WASMs, the actual binary and the gzipped binary, you can find those here. And if you do want to dig into all the crazy stuff under the hood, all the Rust code stuff here. But generally speaking, you can just ignore these things. And that's what the git ignore is for, is we will ignore .azle, we will ignore .dfx, and basically any of these generated type files, so that you don't check them into your GitHub repository. Okay, so that's basically chapter 4. If you want to review that, obviously you can watch this video again, or you can go and read chapter 4 in detail. And we also went through local deployment and how to interact with the canister. Chapter 5, well, actually, I'll pause there. Any questions? I assume there aren't any questions, but if there are, that's a good place to pause. Okay,
So
well, I'll just,
there are a few
go.
questions,
Oh,
but I
okay.
think it's not related to what we just see. Like we can do them later.
Okay.
I'll note all of them and ask you later.
Okay, yeah. Cool. I'll leave like 10 minutes at the end, I guess. Okay, so chapter 5 is all about deployment. If you do have questions about dfx start, stopping your replica, if you run into some installation issues, or not installation, but just some problems, then then go check out chapter 5 for deploying to your local replica. It also explains one more way that you can interact, actually. So we talked about the command line, we talked about the web UI, but there's also all of the agents that you could use. So if you are building like a web application, which I assume you'll be doing for the DAO that you're going to build, you will probably use something called the JavaScript agent or at Dfinity agent. You can npm install this. And like it says here, it is a TypeScript client library for interacting with canisters on the IC. And there are other agents as well, Java, Python, Rust. But the agent is what is going to allow you to make requests from a web browser or some other type of client application to your canister. And it's going to use that Candid file to generate stuff for you and make that really easy for you. And then I'll give you some, there's some more information about the DivX command line if you want to see it here. And finally, deploying to mainnet, which we will not go into in detail here, but it's very, very similar to deploying locally. You basically just add this little network option, but you do need to make sure that you set yourself up with Cycles and get the Cycles wallet, use the Cycles faucet, whatever. And so you can, I guess, follow this link to go to the official documentation to figure all that out. Once you figure that out, then deploying is very similar to deploying locally. Chapter 6, examples. Like I already showed you earlier, this examples repo is just going to be probably very, very valuable for you. So just do not forget about it. And yeah, I just highlighted a few of the examples that you might want to look into. Chapter 7 and Chapter 8, we already kind of talked about these things. We talked about the internet computer and we talked about canisters. I guess we didn't go super in depth. So, I mean, you just saw how to build a very simple canister, right? But maybe to give you a little bit more background information, in the end, your canister is just a WASM module, right? All the compilation that you saw in the terminal was just basically compiling everything down so that it can run in WASM. You have, like we mentioned a long time ago, up to 4 GB of heap. So this global variable right here, message, because it is global, it is stored on the heap of the canister. And the heap is just, I guess, a random access memory location that all WASM modules do have access to. I believe most of them will have access, at least if they're granted it. So yeah, technically speaking, I mean, I guess you could put maybe up to 4 GB in this string, but of all your global variables, just know that you are going to be limited by 4 GB. And then there is a way bigger location called stable memory that gives you up to 64 GB. And we will dive into that a little bit later. I'll probably show you in just a minute. I'll give you a quick preview of that. Chapter 9, if you want to know more about query methods, you can come here. They're really not that complicated, so there's not all that much to say. And chapter 10 is, there's I guess a lot more to say. So if you want to dig into update methods. And then finally, this is where we didn't really get to in our presentation so far, but chapter 11 is all about Candid. So, I mean, everything up to chapter 10 that we just went through, I mean, I feel like you're now, a little bit dangerous with being able to build something. Basically, your canister is just going to be a bunch of query and update methods. And with global variables, you could start creating data structures that you could build your DAO out of. So, you got lots of basics there. And then chapter 11 is really going to let you flush out all of the parameter and return types that you can create and everything. Yeah, basically, how do you go from just primitives, all we talked about were strings, to something more advanced. So let's dive into that real quick. These are all of the types that you basically are going to have available to you in your canister that you can use in your query and update methods and in your stable data structures that we will talk about later. So text is basically string. And by the way, you're going to import a lot of these types straight out of the Azle library. So let's just start showing you how to do that. So let's make a new method. Let's put it right here. Let's make a new query method. And And oops. I'll just show you a couple things. Just that for now. Okay, so we already talked about string. There is an alternative type called text that you can import from Azle. Text and string are basically equivalent. So yeah, it's just there because Candid calls it text. There are also a bunch of number types. So there's something called a nat and something called an int. A nat is a natural number, meaning it's not negative. So 0 to basically arbitrary in size. That's what a nat is. Int can be negative. So int goes way negative and way positive. I don't remember the exact limits on those, but that might also be arbitrary. And then each of these have subtypes or subsets or smaller sizes of these numbers. So you have nat64, nat32, nat16, and nat8. And you have the same with int. Those just let you restrict your sizes. Generally, you are going to want to use the smallest size possible for efficiency purposes. But also, if you just want to keep things simple, you could just use nat or int. Also keep in mind that under the hood, some of these will be big ints, some of them will be numbers. In JavaScript, that's all you have to work with. You only have big int or number. So a nat64 is not going to be just 64 bytes when it's stored in memory. It will be, however big the big int implementation will keep it. And nat32 is not necessarily 32 bytes. It's whatever the JavaScript number type is. But Candid, so when you're interacting with other canisters and people are interacting with yours, Candid will type check these things for you. So if you do have a nat32 and someone tries to pass in a bigger number, I believe that will be a Candid error and it will stop you. So that's nice, I suppose, but just keep in mind that there are some subtle differences there. The blob type is a uint8 array under the hood. So that's how you're going to be passing bytes around. And then probably the most important thing after that would be the record and the variant types. So, and by the way, you just use these types like normal, right? So like param1 could be a nat64, param2 could be a blob, param3, it could be text. Nothing crazy there. A record right here is basically your general purpose object type on the internet computer. A record is going to have basically keys and values. So if you want to make one, just do it like this. And now it's just a normal JavaScript object literal, basically. All of your fields must also be Candid types. So field 1 could be a nat. Field 2 could be a nat32. Field 3 could be a blob, and so on and so forth. Also, these can be nested. So if I want to make another record, then I can make field 3 another record. And so on and so forth. So that's how you're going to be able to create, like I said, the plain data object type. And then the final kind of complex, not the final one, but the very important one is called a variant. A variant is going to be similar to an enum, but it is something that you're probably not used to in TypeScript or JavaScript. It is a special type of enum, I guess you could say, called an algebraic data type. This is a concept that is very familiar if you know Rust or if you are interested in Motoko. Motoko also has this concept. All canisters have the concept of a variant. But a variant is, like I said, basically an enum, meaning if you do have these fields, you can only have, at runtime, when you actually have one of these values, you will only have one of these fields present. So for example, if you want to, let's say you have some like reaction, emoji or something, right? And sorry, generally we will capitalize those for variants. Happy, sad. I don't know, laughing. You can only be, in this case, I guess, one emotion at a time. At least, let's say you're reacting to something. So this will let you choose from only one. If you made it a record, you would have to supply all of them. Also, what's a little bit more powerful than enum is that these can have types as well. So you can put types in if you want, but if you just want it to be an option, then you would just say null. And that is variant. And I mean, that's the basic concept behind your Candid types. You import your types from Azle. You can make complex types with records and variants, and you can use them in your parameters and your return types. And then I guess one more thing I will touch on is the stable data structure that we talked about. So right here, like I said, this global variable is stored on the heap, therefore it is limited to 4 gigabytes. If you need more space, and if you want to make sure that your data does not get erased when you upgrade your canister, so we haven't talked yet about canister upgrades, but every time you push new code, the heap is going to be wiped and your code will be replaced with basically an empty heap. That's okay if you deploy a completely immutable canister that you don't plan to upgrade. But if you do want to maintain control and be able to continue to push upgrades either by yourself or as a group through a DAO or something, then you will need to deal with that. And the way to deal with that is through a memory location called stable memory. And the easiest way to deal with stable memory is to use a data structure called a stable B-tree map. And this is just an alternative to normal map, I guess. A normal map in JavaScript could even just be an empty object, and you could just fit properties in there. Again, it'll be wiped. So if you want to create a stable map, then you just make a new stable B-tree map. You pass in the type of your key and the type of your values, and then you pass in a memory ID here, and then a maximum size for the keys and values. This is all covered, by the way, in chapter 12 in more detail, but I'm just showing you if you're going to be making databases and stuff, you probably do want to be using a stable B-tree map to do it. And this could be my record, and my record could have, for example, an ID field like that. And then book stable map, you could even just call it my records. It's basically now a database table that has a bunch of my records in, right? So yeah, I just wanted to give you a very quick overview of I guess, chapter 11 and 12, because, I mean, yeah, with that information, I feel like you can really go crazy. You can create all kinds of different data structures and kind of database type tables, expose your functionality with query and update methods. And I mean, that is the basic stuff. So I will stop there and answer questions.
Yeah, thanks for the presentation. It was really great. I have noted a few questions. So I know that Dan already answered some of them, but I want to go back to them. So there is one about increasing the speed of update calls. Just want to hear what you think about that. Like, is it possible? How fast can we go? And so on.
You said increasing the speed of the update calls?
Yes, that was the question. Like, how can we increase the speed of update calls? Is it possible?
Yeah, I mean, as a developer, it's really not possible. You are limited by how fast the internet computer can come to consensus. So you are not going to be able to make that faster. There are some things you can do to make sure. So there's just a base amount of time it's going to take, basically. So What you can do though is you can design your canisters in a way to make sure you get that minimum amount. If you do have multiple canisters in your application, you want to make sure you deploy them all to the same subnet. If you deploy one canister to one subnet and another to another subnet, that latency is going to increase even more, maybe around double. So you do not want that to happen. Other than that, though, you need to wait for the protocol developers Dfinity to increase or decrease that latency. But locally, sorry, I should say locally. Let me share maybe one more time. Locally, if you do want to get rid of that delay, you can start your canister up with something called artificial delay, and you can just set that to 0. And that will make it run faster, at least locally. So, FYI.
Cool. Is there a way to determine the language a canister is written in?
To data mine?
A way to determine to know the language.
Oh, determine.
canister.
Yeah.
Yeah.
Yes, but it's not fully developed yet. So there is something called public WASM metadata, and we are working towards putting that information into the metadata of all Azle and Kyber canisters, and we're encouraging the other CDKs to do the same, but it's not a universal standardized solution yet. But in the future, we're hoping that, every canister you'll be able to see what language it's written in by querying that metadata.
Okay. There was someone asking about index.did. So essentially what it is for. And I mean, I think we explained that, but if you want to go back a bit on it.
Sure. Maybe I'll just keep sharing so I can answer the questions. But the index.did file, like I said, it's automatically generated for you. And the did file has a language called Candid written into it, and it represents the interface of your canister. So these did files are used by other clients or other canisters or other tooling to be able to interact with your canister in a very nice way. So you don't really need to think about it too much this week, I would say, because it's going to be generated for you. But just know if you're going to use an agent, if you're going to, you'll see as you develop more and more, there's a lot of tools that will consume this did file to provide functionality to you.
Yeah. And also there is a lecture on Candid. I think it's tomorrow.
Yes, I believe it is tomorrow. So yeah, we'll dive way into that.
And it's Candid is essential for like Motoko canisters or Rust canisters talking to Azle canister. There is a question about principal. So how does principal type work in Azle? Is it just principal?
Yeah, just import principal, and then you just make a principal, and you. Oh no, you don't do it like that. You do. Sorry. Yeah, from text. So yeah, if you have the text, you can do it like that. There's a bunch of methods on here, but yeah, basically it's just this principal class that you import from Azle.
Yep. And I think the person that asked the question is already familiar with the concept, but maybe some person here are not. If you want to explain what is the principle.
Oh, I'll explain what, yes. On the internet computer, basically identifiers are known as principals. So, I mean, it's basically like an ID. So you as a user, if you generate a key pair, the identifier for that will be a principal, and a principal has a private key backing it. I mean, not always, I guess, but your canister IDs are also principals. So anytime you have an identifier for the internet computer, a lot of them are going to be principals, and that is how you give unique IDs to things.
Yeah, I think you have different principles. Like you have the canister ID, the user principles, and there are other identifiers that are like internal to the internet computer. So you have at least 3 of them, and there is also fourth, I think, a fourth, but don't remember the reason. Okay. We had a question about Azle pre and post upgrades. If you want to dive, like,
Okay.
is it possible to use it in Azle and what it is for?
Sure. If you want to do pre or post upgrade, you just import those from Azle. I'll explain what they are real quick. If you do want to know, because we are running out of time, if you go here to the Canister lifecycle, chapter 16. I mean, I guess I'll just use this. So every canister goes through a lifecycle. When it's first deployed, if you mark a function with the init annotation, this function will run when it's first deployed. Every time you deploy after that, your pre-upgrade function will run before your code is changed and before your memory is wiped. And then your post-upgrade function will run after that. So if you want to hook into the lifecycle of the canister, this is how you do it. Why would you do this? There might not be that much reason to do it in Azle because you do have the stable B-tree map. But if you want to save information in stable a location called stable memory without using this stable B-tree map data structure, and just you want to do it manually for some reason, then in pre and post upgrade, in pre-upgrade you could take all of your global variables, convert them into some binary or other format, and store them in that stable memory location. And then in post upgrade, you could read all that out and write them back into your global variables. But generally speaking, I mean, I guess I would not recommend that unless you absolutely have to. That's what the stable structures are for, chapter 12.
Okay. So all the questions with the front end, we will see that tomorrow. There is I'll talk about that in my lecture. And there was a question about pseudograph. I think someone also asked a question about the status of Kybra as well, if you want to quickly mention them.
Yeah, unfortunately, pseudograph we have deprioritized, though in my mind it is still a grand vision to have pseudograph fully production ready, fully integrated into Azle so that, when you make your types, it can generate all that behind. But Azle and Kybra are just taking so much effort. So it's just deprioritized for the moment. And then Kybra is it's in a similar position as Azle. It has some different unique problems, but it's also in beta. You can also use it. You can go to the Kybra book and it's here. There's essentially functionally equivalent with their different trade-offs that they've taken.
Great. Okay. I think we're good.
Okay, awesome.
So next session is in 3 hours. We have the mentorship session. And yeah, that'll be it for today. Thank you. See you.
Yep, thanks everyone. Good luck. Ask questions in the channels. We'll be there.